Now we're going to talk about the formation of solutions in terms of enthalpy. So we're really going to look at the energetics and the heat transfer that takes place as we form solutions. And so I'd like to just kind of revisit what we've done with enthalpy so far in the past and endothermic and exothermic. So we've looked at chemical reactions in detail that were exothermic or endothermic. And so here's an example of an endothermic reaction um, that we may have looked at before. And so we can say that for to form the products, we would need to absorb energy to be able to break and reform enough bonds. There is a net difference between those reactants and products where our products are less stable. And so we need to be able to absorb energy to form them. Now, most recently, we looked at phase changes. We looked at exothermic and endothermic phase changes. So, an endothermic phase change would be something like melting ice, right? Something that went from a solid to a liquid phase. It needed to absorb energy. So, the molecules had enough kinetic energy to move around more in the liquid phase, or going from a liquid to a gas and moving around more in the gas phase. We also saw the opposite of this. That's something that was an exothermic phase change would be going from a liquid to a solid or from a gas to a liquid, where the particles need less kinetic energy. And so it'll release it in an exothermic process. Now we're going to look at solubility in terms of exothermic and endothermic. And we're typically going to see that the formation of a solution is either going to not be endothermic or exothermic. We'll call it ideal, or will form an endothermic solution. And so the process of dissolving ammonium nitrate in water, so we're taking a solid ionic compound and dissolving it in water, is going to be an endothermic process. And that means that the surroundings will get colder. It's taking that energy from the surroundings. And that's what an instant ice pack is. An instant ice pack is just putting an endothermic solution formation on your body, like on your shoulder, and it'll steal the heat from your shoulder and it'll feel cold, right, to you. Now, there can also be exothermic formations of solution as well, where it would release energy and would feel like it got hot, like a hot pack. And sometimes things that, like those little warm things that you put in your gloves when you go skiing or sledding, those are sometimes chemical reactions that are taking place, and sometimes there's solutions forming. Um, and so the instant cold pack example goes along with our endothermic. If it's generating heat and feels hot to you, it's an exothermic process. So let's talk about forming solutions. We call this the heat of solution right here. We call it the enthalpy of solution too. And we've got, they can be exothermic, they can be endothermic. So I have a couple examples here. First, I have an exothermic example, and it's an acid dissolving in water. When we combine acid and water, we actually have a chemical reaction that's taking place that's forming that exothermic, that increase in temperature is where we're actually breaking that hydrogen chlorine bond and forming a hydrogen bond to the water. So it's not quite just a solution, but there's not a lot of exothermic solution formations for me to grab for an example. There's more endothermic reactions. So the one we just saw in the other slide was ammonium nitrate dissolving in water. And that's an endothermic process right here. So, what's happening when a solution is forming? We've talked about we're breaking those intermolecular forces in our solute interactions and our solvent solvent interactions, and then we're combining the solute and solvent and forming more intermolecular forces between them. And so we can break that process down into endothermic and exothermic processes. So to form a solution, kind of the first thing that needs to happen is an endothermic process. And so we'll see that when we break apart the solute particles and the solute particles and solvent particles, it's an endothermic process. That means that we're going to have to absorb energy to make it happen. We're going to have to input energy to break those attractive forces in both cases. And we associate this amount of energy or the heat that needs to be absorbed to be able to make that happen as the enthalpy of the solute and the enthalpy of the solvent, or heat of solute and heat of solvent. Now, as we bring these together and form new attractions, we're going to have an exothermic process. And this is really when we're mixing them. So we call this the heat of mixing or the enthalpy of mixing. And in this process, we're going to be releasing energy. So as we form those attractive intermolecular interactions, it'll stabilize the whole situation and it'll release energy as those interactions form, or those attractive forces form between them. And so if we can break down the process of forming a solution into these three steps, we can calculate a heat of solution or enthalpy of solution from these three separate pieces. So we can say that the enthalpy of the solution or heat of the solution is equal to the enthalpy of the mixing plus the enthalpy of the solvent and the enthalpy of the solute. And so we can break that apart and kind of determine if we think that that enthalpy of solution will require energy to make it form, and then it would be endothermic, or if it would release energy, and then it would be exothermic, or if it'd be zero, and we call that ideal. So let's look at these, or let's look at this a little bit more. So let's look at this. So again, we have our enthalpy of solute, enthalpy of solution, or sorry, solvent, and our enthalpy of mixing. And so both of our solute and solvent enthalpies, this is really about separating or breaking the IMFs of a pure compound. And in our mixing, we're forming intermolecular forces in a mixture. Now, I like the terminology we're using here of enthalpy of solute, enthalpy of solvent, and enthalpy of mixing. But you might see something a little bit different in different textbooks. And that is the enthalpy of mixing is sometimes called enthalpy of solvation, which means the solute is being solvated by the solvent. Ugh, that's a lot of sounds. Solvation is just another way of saying mixing. And so if you run across that, just note that these mean the same thing. So that enthalpy of solvation should be an exothermic process. All right, let's look at examples of the way this can shake out, whether it's endothermic, exothermic, or ideal. And I really like this picture because this helps break it apart in my mind. And so what we have is an energy scale on our right-hand side right here. So this is energy. It's also the enthalpy of the system, right? So if enthalpy is positive, it'll be an increase in energy. If it's negative, it'll decrease down this scale. And so what we start with is this solute and solvent that are just hanging out on their own. And so the enthalpy of the solute, so this step here, step one, is going to be our delta H of solute. That's going to absorb energy to break the intermolecular forces of our solute. And then we're going to need to break those intermolecular forces of our solvent. So we'll add to that the enthalpy of our solvent. And we'll break all of those intermolecular forces. And we'll end up we've inputted a lot of energy and everything's split apart. And then we mix them together. And then as we mix them, that's going to be our enthalpy of mixing. That'll be negative, right? Because it's going to release energy. And so that's going to bring us back down. Now, if the amount of energy we have to put in to break the intermolecular forces of our solvent and our solute is the same as the energy we release to reform intermolecular forces between the two, then we'll have no real net change in energy, right? Like we won't need to absorb energy to make this happen or release it. And so we'll have kind of the same energetics before and after. And so we'll call this an ideal solution. And this happens when we have intermolecular forces in our solvent and solute that are identical, because it means they're going to break the same exact ones that they're going to form with each other. It's not exothermic and it's not endothermic, which is interesting, right? It's just is. So let's look at it when it's not ideal. And let's start with exothermic. So again, we have our enthalpy of solute first, followed by our enthalpy of solvent. And we're putting all this energy in to break these intermolecular forces. And then when we combine them and we see how the solute and the solvent interact with each other, and it lowers, so then it releases energy, it'll lower it on the energy scale right here. And if it releases more energy than it was required to be used to break those intermolecular forces, then we'll have a net overall release of energy in our system that really is just this part right here. This difference will be our enthalpy of solution. That little difference right there between our beginning and our end. And so this is going to occur when our solute and solvent intermolecular forces are actually stronger than the solute and solvent. And so that stronger is kind of the key word. So if we're able to form stronger interactions between the two different molecules than they were forming with each other, and maybe this is like the creation of a hydrogen bond to one, right? It's less common to do this. It's easier to form ones that are not as strong. But we'll see then an overall release of energy, and we would call this exothermic. Now, looking at the most common version of this, the endothermic case, again, we first see our enthalpy of solute here in step 1, our enthalpy of solvent as step 2, and we're putting all this energy into separating them, and then we bring them together. And when we bring them together, our enthalpy of mixing is not going to release as much energy as we had to absorb to break those intermolecular forces in the first place. And so that net difference between beginning and end, that enthalpy of mixing, is overall positive. So we have an endothermic process. We're going to see this occur whenever our solute-solvent interactions, our intermolecular forces, are weaker than the solvent-solvent or solute-solute added up together. And so this is a little bit more common. It's common, especially if you have like an ionic compound. Ion-ion interactions are very strong. And if you're replacing them with ion dipole interactions, lots of them, it could definitely compensate for a lot of the energy that had to go into break the ion-ion interaction. But it's not going to be quite as strong. And so we'll see that it actually requires some energy to be absorbed to make that happen. And if it is too large of a difference, if it's too endothermic, then we won't be able to overcome that energy barrier just by the tendency to mix and the increase in entropy we get by bringing these two together. And then we'll see that a solution doesn't form. We'll just see an insoluble compound, or just a little bit of it forms that isn't all of it.